All right, our final weekly reading question has to do with the Pleistocene glaciations. So what type of, let me just fill this in real quick. What types of geologic evidence are there that tell us that there have been glaciations during this Pleistocene period, which is the most recent few million years? And so pretty straightforward. These striations that you can see on bedrock from where a glacier basically rode over the top of the bedrock and shaved everything off. There are also glacial moraines, which are basically piles of dirt left over on the sides and the end of a glacier, where a glacier, once the glacier melted. Glacial till, which are mixtures of different types of sediments of various types and sizes. And then, of course, the famous loess, the windblown dust, of which the Palouse region is one of the few places on Earth where you can find this. So these rolling hills of the Palouse are dust that was blown here from the Puget Sound area over the last couple millions of years. So those are geologic evidence of glaciers. What causes the change in the oxygen isotope composition of seawater? The primary cause of the change in the oxygen isotope composition of seawater is the amount of water in the ocean. So during glacial times, water is transferred from the oceans to continental ice sheets. As it gets colder, ice sheets are able to form in the northern regions, and so or in the poles. And so as you build up this ice volume in continental glaciers or continental ice sheets, the sea level goes down. And as that sea level goes down, the heavier isotopes are left behind during that evaporation process. So the seawater becomes what they say is enriched. Becomes enriched with water that has oxygen 18 atoms, and so that's the primary thing. During glacial times, water is transferred from the oceans to the continental ice sheets like Antarctica, Greenland, and the Laurentide ice sheet. And when this occurs, the heavier isotopes are preferentially left behind in the ocean. Thus, the concentration of water containing oxygen 18 goes up during glacial times and down during interglacial times, which you can see from that graph of the oxygen isotope in the book that we talked about. What are the three characteristics of the Earth's orbit around the sun on the timescales that vary on the timescale of the Pleistocene glaciations? Those are the eccentricity, which has a timescale of 100,000 years, the obliquity, which is also another word for the tilt of the Earth, and then the final one is the precession. And the precession is basically the fact that the closest approach of the Earth to the sun changes on this time scale. This is 100,000 years, 100,000. This is about 41,000, and this is about 20,000 year time scales. Okay. And the degree to which these parameters affect incoming solar radiation is shown in figure 14-8. And note that the precision and the obliquity show significant changes in the amount of summertime insolation at 65 north, so high northern latitudes in summer. But the eccentricity does not. And so that becomes really important in trying to explain these Milankovitch fluctuations. Remember that this is from the Milankovitch theory. This minute I'm going to have to move this up here so I can write. These were the things that were proposed by Milankovitch, and the effect on sunshine. And what orbital configuration favors glaciation, and why? The orbital configuration that favors the amount that the configuration of these three parameters that gives a low amount of summer insolation in the northern hemisphere. That would be a large eccentricity, so large eccentricity, an aphelion in the perihelion in the perihelion in the winter, like it is now. So the closest approach is occurring in winter. Right now, currently the perihelion is in January, so we're closest to the sun in winter, which would also give us low summertime sunshine. And then finally, the tilt, a large tilt, because large tilt gives us greater seasonality. If we didn't have any tilt to our Earth and our orbit, we would have no seasons. And so if we have more and more, a greater tilt, we have more seasonality. So those are the configurations. Anything that causes the basically the combination of all these that gives low sun in the northern hemispheric summer, because we believe that the northern hemisphere is very, very important. That Canada, that's a period, or that's the place where the ice sheets can form, the Laurentide ice sheet. Okay, what role do biologically produced sulfur gases play in climate fluctuations? That's pretty easy, because we know that aerosols or any kind of junk in the atmosphere actually causes the albedo to be greater. And so certain types of biological activity in the ocean produce sulfur gases, and in particular one is quite important, this methane sulfonic acid, MSA. These can create aerosols. So a greater amount of MSA in the atmosphere will cause increases in aerosols, and so if MSA goes up, aerosols goes up, this increases the albedo, which then decreases the surface temperature. So this can cause cooling. This is a positive feedback cycle. So during glacial times, ice cores show more MSA in the atmosphere, which tends to cool the planet even more. And you can see this in figure 14-9. What factors might have caused atmospheric CO2 variations that kept pace with glacial climate fluctuations? So there are quite a few factors that were talked about in the book, and the following are ones that could have helped. The role of the biological pump, the shelf nutrient hypothesis, the iron fertilization, the coral reef hypothesis, and the terrestrial biomass. So these factors help to change the biological activity in both the ocean and on land. So the biopump, the shelf nutrients, that hypothesis and the feedback associated with that, The iron, this is the chemical symbol for iron fertilization. Fertilization. The coral reef. Coral reefs might have had effect. And the terrestrial biomass. Okay, now explain why the formation of North Atlantic deep water, this is our NADW that we've talked about a couple times, might have played a role in causing the Younger Dryas. So the Younger Dryas was this cold period that occurred about 10,000 years ago. So we were transitioning from a glacial time. We were starting to warm up into an interglacial, and the Younger Dryas was this time period where the Earth got cold, or at least the northern hemisphere got cold again, and started to cool off, and then we went into a more current interglacial time. So this was about 10,000 years ago. And it was called the Dryas because the Dryas were a particular type of flower that they found in Europe that only grows under certain conditions. So the formation of the NADW, the North Atlantic Deep Water, helps to drive the thermohaline circulation. So when this water sinks in the North Atlantic, it kind of pulls the Gulf Stream up. If I just draw a little picture of this would be the coast of the U.S. And if this is the North Atlantic up here, currently the Gulf Stream waters get pulled along up here in the ocean gyre. This is the Atlantic gyre. But up here, this water is sinking down. It's sinking at this place, and so it helps to pull this up. If this shuts off, which we think occurred during the Younger Dryas, the Gulf Stream peeled off and didn't go all the way up to the North Atlantic. And so it got cold up here. And because this warm water was not going north and it was staying south. And so, if the North Atlantic Deepwater Formation is strong, so it's sinking in that area, this promotes strong transport of warm saline water to the North Atlantic by the Gulf Stream. That would be this situation right here. If there is a large influx of fresh water into the North Atlantic, for instance, let me just grab a blue pen here. If we had a large influx of water from these glacial lakes that were sitting up here near the Great Lakes, that would freshen this water and it would cause it not to sink so much. And then we would be in this situation where the Gulf Stream would not go as far north. So if the NADW water formation decreases, the Gulf Stream transport also weakens, which causes Europe's temperature, this temperature over here, to get cold. This is what scientists believe actually caused the Younger Dryas. And in fact, we believe that there are indications that this water in this area, again, is freshening. At this time, so there are concerns that the North Atlantic deep water is slowing down currently. Alrighty, that's it for the weekly reading questions. I'll post this, and hopefully you'll find some use for it. Okay, bye.